Hello and welcome to my series of videos on prime numbers. Today we're going to look at the number 1, which is classed as not prime, and I'm going to present a couple of arguments as to why that's the case. So let's get cracking. So we have the classic definition that a prime p is only divisible by 1 and itself, i.e. p equals 1 times p or p times 1. Example, 17 equals 1 times 17. So 17 is prime. 17 has no smaller factors between 1 and 17. Consider the general definition again. Let's be more specific. Let's actually let p equal some known prime. You'll see what I'm trying to do in a minute. So we know 17 is prime and we can easily verify it. So let p equal 17 in our general definition. So we are making our general definition specific. We are choosing p equals 17. So the specific definition will be a prime p equal to 17 is only divisible by 1 and itself 17. A prime p equals 17 is only divisible by 1 and itself p equals 17. So a prime p is only divisible by 1 and p. Or a prime p is only divisible by 1 and a prime p. Or if you put it another way, 1 times a prime number equals a prime number. The prime number being the same in both sides of the statement. It's kind of obvious. 1 times something is something. 1 times 10 is 10. 1 times 99 is 99. So argument 1. Take any prime p greater than 1. Example, p equals 7. Then 7 times 2 equals 14 and 7 times 3 equals 21. Clearly 14 and 21 are composite, i.e. not prime. Now suppose p equals 1 is prime. Repeat the argument that we did with 7, multiply by 2 and 3. So 1 times 2 equals 2, 1 times 3 equals 3. But 2 and 3 are prime. They're not composite. With 7, when we multiplied by 2 and 3, we got composite numbers. But with 1, we get prime numbers. So for p equals 7, we had 14 and 21, both composite. For p equals 1, we have 2 and 3, both prime. In fact, 1 times any prime p greater than 1, is prime. And 1 times any composite, c greater than 1, is composite. Might not be obvious at first, but yeah, when you think about it, it's pretty obvious. 1 times anything is anything. It doesn't change the thing that you're multiplying by 1. But any prime p greater than 1 times any other number n greater than 1 is always composite. Example, 7 times 2 equals 14, 7 times 6 equals 42, 7 times 13 equals 91. 14, 42, 91 are all composite. But this fails for 1. Example, 1 times 2 equals 2, 1 times 6 equals 6, 1 times 13 equals 13. 2 and 13 are prime, but 6 is composite. So if a and b greater than 1, then ab is composite. But if a is 1, then ab is not guaranteed to be composite. It's only composite if b is composite, since 1 times prime equals prime. This is kind of obvious, as 1 times anything is just anything. Multiplying something by 1 doesn't change it, as 1 is the multiplicative identity. You will learn this in abstract algebra courses. We won't cover that in this video. Argument 2. Let's look at arithmetic progressions. I'm not going to discuss arithmetic progressions in any great detail in this video. I'm just using them to present the argument that 1 is not prime. So I'll write APs for short. AP means arithmetic progression. Let's consider a few arithmetic progressions with first term and common difference a, which is a prime number. Example, let A equal D. D is the common difference, equals 2. So note A here is our first term, but we're also making it equal to our common difference, which is 2. And the numbers in red, 2 and 3, are prime numbers. So it's very important that that first number is a prime number. And then we will also be using that as our common difference. You'll see what I mean in a second. So AP2, I've just called it AP2 for convenience. So yeah, AP2 is 2, 4, 6, 8, 10, 12. So an arithmetic progression is just a series of numbers with a common difference. First term and a common difference. The first term here being 2, which is prime, common difference of 2, which is also prime, which is also equal to the first term. And then if you look at AP3, it's the same idea, only 3 is the first term and 3 is the common difference. And that gives us 3, 6, 9, 12, 15, 18, etc. Let A equal D equal 5. AP5 is 5, 10, 15, 20, 25. Again, 5 is prime. Do for 7, A equal D equals 7, or AP7 is 7, 14, 21, 28, 35, and so on. So far all the first terms in these arithmetic progressions are prime numbers. So let's gather them together. So AP2 is 2, 4, 6, 8, 10, 12, 2 is prime. AP3, 3, 6, 9, 12, 15, 18, 3 is prime. AP5, 5, 10, 15, 20, 25, 5 is prime. AP7, 7, 14, 21, 28, 35, 7 is prime. So the red numbers are prime. Right. Now watch what happens when we consider 1 in this manner. AP1 is 1, 2, 3, 4, 5, 6, 7, 8. So 1 is our first term and 1 is our common difference. We're following the rules we followed for 2, 3, 5, and 7. So let's put them together. So now I'm putting 1, 2, 3, and 5 together. There's not enough room to put 7. But don't worry about that. We can still get the point. So AP1 is 1, 2, 3, 4, 5, 6, 7, 8. We've already looked at 2, 3, and 5. Now I've put the number 1 in green. The reason I'm doing that is because I'm claiming, or I'm saying, that 1 is not prime. So I don't want to put it in red. I'm putting my prime numbers in red here. Now all the red numbers are definitely prime. There's no question about that, no confusion or ambiguity over that. But I've put 1 in green because I'm saying that 1 is not prime. We can't call it prime. The black numbers, they're all composite numbers, apart from 2. Don't worry about that. Don't worry too much about 2 at the moment. The reason 2 is black in the first series is because I've just left the even numbers black. So don't worry too much about that. That's not important at this moment. So AP1, as I say, is 1, 2, 3, 4, 5, 6, 7, 8. And I've already done the other 3 sequences. Now, with 2, 3, and 5, it's pretty obvious. You can see that the first terms are prime, but all the other numbers are not prime. They're composite. But AP1, this throws up a problem. AP1, we have 1, 2, 3, 4, 5, 6, 7, 8. This is unlike the other arithmetic progressions. All numbers after the first term are clearly not composite. Not only that, the first term is 1, which for all intents and purposes is not even prime. And this is what this video is about. This is what we're saying. So let's go back up again. So 1, I'm saying, is not prime. Some people may disagree. 2 is definitely prime. 3 is prime. 4 is composite. 5 is prime. 6 is composite. 7 is prime. 8 is composite. Every even number greater than 2 is composite. So they're all out. But not every number after the first term is composite. And that's what happened with the other sequences. But it doesn't happen with 1. With 1, we can find many, many prime numbers. And As we know from the prime number theorem, there are infinitely many. This was proved by Euclid. You can look it up. We're not going to discuss it here. So yes, that arithmetic progression will have infinitely many prime numbers in it. So therefore, not all of those numbers will be composite. So that arithmetic progression does not follow the same logic as the other ones that we looked at, 2, 3, 5, and 7, etc. So this is the issue with 1. So as I said, we were supposed to give arguments why 1 is not prime or cannot be classed as prime. So I hope these two arguments are enough to show you that 1 cannot or should not be classed as prime. So thanks for watching, and please subscribe to my channel.